Welcome back to Data Explained. Today, Episode 7, Rate Limiting, the quiet little gatekeeper sitting in front of almost every API you've ever used. We're going to unpack how services protect themselves from abuse, from accidental overload, and from those nightmare cloud bills, all by politely telling clients to slow down. So let's start with the pain. Without any limits in place, your API is wide open. And that's fine until a buggy script, an aggressive scraper, or a genuinely malicious actor decides to hammer it. Suddenly, servers buckle. Legitimate users get a degraded experience because of one bad neighbor, and your cloud bill quietly grows teeth. The fix is almost embarrassingly simple in concept. Cap how many requests each client can make in a given time window, and turn away the excess. That, in a sentence, is rate limiting. Let's make that definition concrete. The shape of the rule is always the same, a cap tied to a specific client, measured over a specific window. So you might say something like 100 requests per minute per API key, and the moment a client crosses that line, the server stops playing along and politely returns a 429, the HTTP code that literally means too many requests. That's the entire mechanism in a nutshell. If that still feels abstract, picture a nightclub. The venue has a safe capacity, and the bouncer at the door lets people in at a steady pace. Once it's full, new arrivals just wait outside for a moment. Nobody's blacklisted. They're simply told, "Not right now." That's exactly what your rate limiter is doing. The request limit is the capacity. The limiter is the bouncer. A 429 is the polite "wait outside," and the retry delay is when guests are welcome to try the door again. Let's see that bouncer in action. When a client is under the limit, the request flows cleanly through the limiter, reaches the API, and comes back with a healthy 200 OK. Everyone's happy. But once that same client crosses the threshold, the limiter steps in and stops the request right there. Nothing reaches the API, and the client gets a 429, the standard HTTP way of saying, politely but firmly, "You've hit the limit. Slow down." So how does a limiter actually decide who's over? The most classic approach is the token bucket. Picture a bucket that's slowly refilled with tokens at a steady rate, say 10 per second. Every request that comes in spends one token. If there's a token available, the request passes. If the bucket's empty, it gets refused. The elegant part is that the refill rate sets your sustained limit, while the bucket size quietly allows short bursts when traffic spikes. Token bucket isn't the only game in town, though. Its cousin, the leaky bucket, drains requests at a fixed rate instead. Great when you need smooth, predictable output downstream. Then there's the fixed window, which just counts n requests per clock interval. Dead simple, but it suffers from spikes right at the edges. The sliding window fixes that by rolling continuously, giving you fairer accounting. Still, token bucket remains the sensible default. It handles real-world bursty traffic without breaking a sweat. Let's zoom in on that edge problem because it's the classic gotcha with fixed windows. Picture 100 requests per minute limit. A client fires all 100 at 0:59. The clock ticks over, and they immediately fire another 100 at 1. That's 200 requests in roughly 2 seconds, double what you intended. A sliding window sidesteps this entirely by always looking back across the last 60 seconds, no matter when you check. It's smoother, fairer, and much harder to game. Now, once you've picked your algorithm, there's a second question that's just as important. What exactly are you counting against? IP address is the simplest hook, but shared networks and proxies muddy the picture. API keys or user accounts are usually fairer since each customer gets their own budget. You can also tighten limits on specific endpoints, say an expensive search route, and layer a global cap on top to protect the whole service. In practice, mature APIs mix all of these together. So once you've decided to turn someone away, how do you actually say it? The web has a standard answer, a 429 too many requests response. But the real courtesy is in the headers. You tell the client their limit, how much they have left, and crucially, a retry after value. so they know exactly when to come back. That last one turns a frustrating wall into a simple try again in 30 seconds, which well-behaved clients will happily respect. Now, where does this logic actually live? You've got options. The API gateway sits at the front door, stopping excess traffic before it even reaches your app. Middleware inside your app works too. Every request checks a counter, but once you scale to multiple servers, you need a shared store like Redis. Otherwise, each server is counting on its own and your limit quietly multiplies. And for really nasty floods, the CDN or edge can block them far from your origin. So why bother with all this plumbing in the first place? 4 big reasons. It blunts abuse, your brute force attempts, scrapers, and outright floods. It protects logins by throttling password guessing before someone walks in. It keeps your cloud bill from spiraling when usage spikes. And it enforces fairness, so one greedy client can't starve everyone else. Reliability and security in one control. That's why every serious API ships with it. Before we go deeper, let's clear up a few myths that trip people up. Rate limiting doesn't stop attackers cold. It slows them down and buys you time, but you still need real DDoS and auth defenses behind it. A single global limit isn't enough either. Without per user or per IP caps, one noisy client can drain the whole budget. And counting requests in app memory falls apart the moment you run more than one server. For accurate limits across a fleet, reach for a shared store like Redis. So how do you actually do this well? When a client crosses the line, tell them, return a 429 with a retry after, and send rate limit headers so they know where they stand. Silent drops just confuse people. Tune your limits per endpoint with stricter caps on logins and writes than on simple reads. Back it all with a shared store like Redis, and set the numbers loose enough that real users never notice. Only the abusers do. Now, you almost never have to build this from scratch. Nginx ships with limit rec baked right in. Redis is the go-to for shared counters when you need distributed limits across many servers. API gateways like Kong, AWS, and Apogee handle it at the edge of your platform, while Cloudflare pushes it even further out to the network edge. Envoy covers you inside a service mesh, and for quick wins, library middleware like Express Rate Limit drops straight into your app. So let's pull the main threads together. Rate limiting caps, how many requests a client can make in a given window. And when they cross that line, you politely refuse with a 429 and a retry after hint. Token bucket is the sensible default because it tolerates short bursts, and in practice, you'll layer limits by user, IP, and endpoint rather than picking just one. And the moment you scale past a single server, remember your counters need to live somewhere shared, which is where Redis earns its keep. And that shared counterpoint is a nice bridge because rate limiting really does touch every layer of the stack we've covered in this series. It usually lives at the API gateway, where it's the natural choke point. It shows up in auth, throttling login attempts, so attackers can't just guess forever. It leans on Redis for those shared counters across servers, and it pairs beautifully with message queues, which absorb whatever work the limiter does let through. One concept, networking, auth, and data. That's why it's a system design staple. If today's episode clicked for you, the rest of the Data Explained series is right there waiting. Indexes and ACID, sharding and caching, message queues, and plenty more system design fundamentals that connect back to what we just covered. And if you want to go beyond rate limiting into the full picture of API defense, auth, validation, monitoring, a properly hardened gateway, that's all over at dargslan.com courses. Before we wrap up, I'm curious, have you ever been rate limited by an API yourself? That dreaded 429 popping up right in the middle of a project, usually when you're demoing something or shipping on a deadline. And on the flip side, when you build your own APIs, how do you draw the line? Per user, per IP, or something more clever, like a token bucket tied to API keys? Drop your approach in the comments. I genuinely want to hear how you're solving it. And that's rate limiting. Hopefully, it finally clicked from the floodgate problem all the way through to the token buckets keeping things civil. If this episode helped, hit subscribe and stick around for the rest of the Data Explained series, where we keep unpacking the infrastructure ideas that quietly hold the internet together. You can also find more over at dargslan.com. Thanks for watching. I'll see you in the next one.